Hi group, it's Mrs. Schaus here, ready to take a look at notes from section 1.8. Notice that we are going out of order, so I want to make sure that you're looking at the right section. For now, we're going to be learning to solve inequalities in one variable. And when I say learning, I will say that something as simple as solve a linear inequality in one variable should be something that you already know how to do from Algebra 1 and again from Algebra 2. You may even recognize these latter couple nonlinear inequalities or absolute value inequalities as we work through them. But I did carefully want to make sure that we study them because, again, of the way that we ended the spring kind of abruptly and knowing that some of you may not have really had sufficient time to study those pieces. All right, in thinking about solving a linear inequality, you can look back on page 82 of your text if you like to remember rules of linear inequalities. But I think, basically we understand that for a linear inequality, we solve the same way that we would a linear equation with one exception, which is if we multiply or divide by a negative, then we have to switch the direction of the inequality symbol. So I'm going to subtract 11x from each side because, again, my goal is to get all of the variables collected on one side. And similarly, I'll subtract 6 from each side because I want to get all of the constants on the other side. At this point, I need to divide by -6 to finish isolating x, but you heard it, I'm dividing by a negative. So I want to keep the x, but I'm going to switch the direction of the inequality symbol, and this quotient equals -2. So my solution set for this inequality, it's not like an equation where in a linear equation we solve and there's one number that makes the equation true. There's a set of numbers that will make this inequality true. And it's all real numbers that are greater than or equal to -2. All right, we're going to take a quick look at solving a linear simultaneous inequality. That is sometimes dubbed as a sandwich inequality. We sort of got two different inequalities here. There's one sitting there. 18 is less than 2x plus 4. And also 2x plus 4 is less than or equal to 28. You can see why we call it a sandwich. This piece is sort of sandwiched in between the two inequality symbols. So since I'm solving this inequality at the same time that I'm solving this one, I'm going to subtract 4 here and here so that I can solve this inequality. And then I'm going to subtract 4 from each side here and also here to solve that second one. Sorry about the barking dogs in the background if you heard that. Okay, that leaves me with 24 sitting here. And now to finish solving for x, I'm going to divide by 2 in each of the pieces for similar reasoning. 7 is less than x, which is less than 12. All right, let's take a look at nonlinear inequalities. And in order to do that, I did suggest that you maybe take a read through your text. There's some additional examples that might be helpful. I'm going to take sort of a graphical approach to what I do. You can write up basically the same line of thinking, but using a table instead, and some of you might prefer that. It's up to you. All right, so sort of step one here is that I'd like to collect all the terms on one side if they're not already there. In this instance, they are. So I've got nothing left to sort of bring over to the left side. The reason that I want to do that is because I would like to be able to factor this and compare it to 0. All right, so in order to factor it, let's see, I'll have an x here and here, plus 4 and -2 will do the job. I'm going to write over here that my first step, beyond collecting the terms on one side and factoring, is to find the zeros. Now, that means that I want to know values of x that make this and also this equal to 0. You probably could write a little bit of work here to support that. So I get x equals -4 as one of my zeros, and x equals +2 as the other. I mean, the reason I care about zeros here is that if I'm looking at numbers that are one side or the other of a 0, that's going to determine where I have a positive factor or a negative factor. Okay? So now the next step then is to make a number line. And on that number line, we're going to create or make intervals. So here's my number line representing all real numbers. I'm going to put my zeros, -4 and 2, on the number line, and it separates the set of reals into 1, 2, 3 intervals. The third step is to test the intervals. Now, the cool thing about these intervals is that if you test and it makes this inequality true, every real number here would make the inequality true. If it makes it false, all of them will make it false. All right, so if I'm going to test something in this interval, -infinity to -4, essentially, I want it to be something easy to test. So let me pick like -5. Something between -4 and 2 to test, how about 0? And something bigger than 2, let's do 3. Now, when I say I want to test these, what I mean is I would like to plug in, I'm going to start with the -5, plug in that value in place of x, both here and also right here. And then I want to ask myself, I'm going to put a question mark here, is that really greater than 0? Well, I could simplify each of these and figure out the numeric value to decide if it's greater than 0. But since we are comparing to 0, it will be as simple as knowing, is it a positive number or a negative number? So I'm going to look at this grouping, -5 plus 4, that's -1, but I'm not going to write -1. I'm just going to write down that it's negative. -5 minus 2 more, that's again negative. Whoops, negative. Okay, and so now I'm asking myself the question, is a negative times a negative greater than 0? Well, that would be positive, and anything positive is greater than 0, so yes, that holds true. That means that all of the numbers down here in this interval make this inequality a true statement. We'll talk about the endpoints in a minute. Let's test that number between -4 and 2. 0 was what we were going to use. So I'll plug in 0 for the x, both here and also here. And again, there's a question mark above this greater than piece. Is that greater than 0? Well, I've got a positive here, a negative here. And is that going to give me something that's greater than 0? I would get a negative result, and that can't be greater than 0, so that is a no. It does not work. And I'm going to cross off that as a piece of my solution set. It is not a piece of my solution set. I've got one more to test, the 3, and see if that, in fact, is greater than 0. Here I get a positive 7, so positive. 3 minus 2 is a positive 1, right? And again, is that greater than 0? Of course it is. So that also checks. All right, as far as the endpoints are concerned, I can never test the endpoints. But in the end, I may or may not need to include them. To decide if I include them, I look at the original inequality and I say, oh, this says strictly greater than 0. If -4 and also 2 can be plugged in to create something that exactly equals 0, then I don't want to include them. I'll leave them hollow. But if I had an equal part here, I would shade those in to include. Okay? Now, the last piece is that not only did I want to represent that solution set graphically, but I would like to do so in interval notation just to represent all of the real numbers that are solutions to this inequality. Everything between -infinity and -4, but also I want to include things, so I'm going to use a union symbol between 2 and positive infinity. Okay, let's take a look at another nonlinear inequality. This one looks a little different than the last one. It's rational. Okay, don't forget step 1. Step 1 was to collect everything on one side. I'm going to move over here so I have sufficient space. So I've got x plus 1, it's supposed to be a plus, over x plus 2. And if I bring this term to the left-hand side, I'm going to have minus x over x minus 1 is greater than 0. Yeah, I always want to, kind of compare to 0. So collect everything on one side. Now, because this is a rational expression, in order to be able to subtract or combine them, I've got to have a common denominator. So I need a factor of x plus 2 and a factor of x minus 1 in that denominator. So this first term is going to get multiplied by x minus 1 on top, and also x minus 1 on the bottom. This second term needs to be multiplied by x plus 2 over x plus 2. All right, so now I've got a common denominator. I can put these together. I'm going to actually multiply this out, so that'll give me an x squared plus 1x minus 1x. Those cancel each other, but then I just get a minus 1. And then from that, I'm going to subtract what I get when I distribute this x through. So x squared plus 2x. Maybe you could distribute that negative sign through at the same, in the same step. That's up to you. And here's my common denominator, x minus 1, x plus 2. Just forgot my grouping symbol there. All right, that is greater than 0. All right, now, again, if I think about cleaning this up by combining like terms, what I would really have, I'm going to try to squeeze that in maybe right here. I would get x squared minus an x squared. Those would cancel. But when I distribute here, I would get negative 2x, and then I've got that negative 1 here, all over x minus 1, x plus 2. And that it needs to be greater than 0. So there's the inequality. That looks like an arrow. Let me erase and try to clean it up a little bit. Greater than 0. Okay, so there's the inequality that I'm trying to, sort of manage in a cleaned up sense where I'm comparing it to 0. I want to run through the same steps that we did in the last problem. So for step number 1 here, I want to find zeros. But there's a little bit more to it when it's a rational expression. Not only do I want to find zeros, but I want to find undefined values. That is, I want to find the values for x that create division by 0. All right, let's start with the 0 itself. What's going to make a fractional value equal to 0 is when the numerator is 0. So I'm going to work off to the side here since I don't have a lot of space. Negative 2x minus 1 equals 0. I'll add 1 to each side. Divide by negative 2. So negative a half is my true 0. The values that are going to make the undefined, the expression undefined, are going to be positive 1 and negative 2. Okay, so step 2, let's plot those on a number line. Here's my negative 2, my negative 1/2, and positive 1. I've got 1, 2, 3, 4 intervals to test this time. All right, let's test negative 3. Maybe I should put down, we're testing here, right? Testing intervals. So negative 3. Between negative 2 and negative a half, how about negative 1? Here, let's test 0. And bigger than 1, how about testing 2? And because I don't have a lot of space, let me try to show the test off to the side here. So I'm going to put in negative 3 in place of x in each of the 3 places. Now this time when I do that, I'm going to have a positive or negative number in the numerator and 2 different factors that could be positive or negative in the denominator. And we're going to use that to compare this whole expression to 0. All right, if I put a negative 3 in here, I get positive 6 minus 1. That's going to be a positive value. In the denominator, when I put negative 3 here, I get a negative. And then down here, negative 3 plus 2, that's another negative. A negative times a negative will give me a positive. So positive over a positive will be, in fact, greater than 0. That part does work. And so I'm going to shade everything here. All right, let's try the negative 1. If I put a negative 1 here, I get 2 minus 1, which is still a positive number on top. Negative 1 minus 1 is going to give me a negative number down below. Negative 1 here plus 2 will give me a positive value here. So now in the denominator, if I multiply a negative times a positive, I get a negative. A positive divided by a negative will not be greater than 0. This is a no. So I'm going to exclude that piece. Let's try the 0. 0 in here leaves me just with negative 1 up top, so I'll have a negative up top. In the denominator, if I have a 0 here, I'll have a negative, and here I'll have a positive. Once again, though, this will be a negative denominator. A negative over a negative will give me something greater than 0. It'll give me a positive. So that piece works as well. Let's see. That was testing the piece from -0.5 to +1. Okay. And in the last piece to test 2, when I put 2 in here, I get -4 minus 1 more, but leaves me with a negative up top. If I put in 2 here, 2 minus 1 gives me a positive value down below. And 2 plus 2, that's another positive value down below. A negative divided by a positive is not greater than 0. So again, that piece is a no. So this piece does not work. So you can see my solution set again graphically, but I could state it -infinity to -2. And again, that's coupled with the interval from -0.5 to +1. Notice that once again, I'm not including my endpoints, and that's because this says strictly greater than 0. Even if this had said greater than or equal to 0, that does not mean I would automatically include all endpoints. It means I would include the one that is a 0, the -1/2. I never include values that create division by 0. So that was the second of our solving nonlinear inequalities. Let's take a look at a couple that are absolute value inequalities. All right, so you should have studied these really in Algebra 1. And in studying these, you probably learned a little trick that was if your symbol says great or, you connect with the word or. And if your symbol is less than and, you connect with the word and. Okay, so greater than, we use or. Less than, we use and as a connecting word. All right, so in this first one, we're going to write two pieces. One is x minus 1 divided by 2 is greater than 5. It's great or, so we connect with the word or. And the or piece is the same piece that's inside the absolute value symbol, but this time we switch the direction of a symbol and we make the 5 a negative. Okay. So now we want to go through and just solve each of these two pieces. I can multiply by 2 on each side. That leaves me with x minus 1 is greater than 10. And I'll add 1 to each side. So x is greater than 11. Or, I got that or word connecting. Again, here multiply by 2 on each side. So I get x minus 1 is less than -10. And if I add 1 to each side, I get x is less than -9. So if I wanted to graph that, I'm looking at values that are less than -9 or values that are greater than, strictly greater than, right? +11. So there's a graphical representation of my solution set. Remember that or is a union. So it's putting together of these two pieces. They don't have to overlap. The word and is an intersection. One more absolute value inequality. Remember that if the absolute value is not isolated, if there are operations outside of it, that we need to clean that up first before we break it into its two parts. So I'm going to divide by 2 on each side, and that'll leave me with the absolute value of x minus 2 over 4 is less than 4. And since this is a less than, we're going to use the and connector here. So I've got x minus 2 over 4 is less than 4, and x minus 2 over 4 is greater than, I'll switch not only the direction of a symbol, but the sign here, so -4. And I solve each of those two pieces. Here, I'll multiply by 4 on each side, so I get x minus 2 is less than 16. And now I'll add 2 to each side, so I get x is less than 18. And here, multiply by 4 on each side. X minus 2 is greater than -16. If I add 2 to each side, I get x is greater than -14. So this entire statement is my solution. Now, if I think about that graphically, think about what this piece says. It says all x's that are less than 18. That would be this piece. This one says all x is greater than -14. That would be this piece. But because it says and, which is an intersection, Graphically here, I'm talking about only these overlapping parts, so between negative 14 and positive 18. You could write the solution set this way, or you could write it with the and statement. Either one would be fine. We've got one last example to look at. I'm going to take a look at an application. So solve an inequality for a real world problem. It says a parking lot charges $10 per day plus 50 cents per hour for plan A. So I'm going to write down an expression for plan A. And then $2.50 per hour for plan B. So we'll write an expression for plan B. Let's do that first. So the cost here for parking in lot A is $10 for the day plus 50 cents per hour. And the cost over here for plan B is $2.50 per hour. It's nothing, for the day, but $2.50 per hour. And what we want to know is for how many hours is plan B cheaper? So we want to know when 250H plan B is less than what it costs for plan A, $10 plus 0.50H. I think you can see that if you're going to park for a small amount of time, you'd rather go with plan B. But longer periods of time, plan A could be cheaper. So we're going to go ahead and solve this for H to find out how many hours it would take. So let's see. If I subtract 50 cents H, 0.50H from each side, I get 2H is less than 10. And if I divide by 2 on each side, the number of hours would have to be less than 5. Okay, the dogs are getting restless. I'm sure you can hear that in the background. Sorry for that interruption. I hope this helps you folks in trying to solve these various inequalities. I'm going to go ahead and stop the tape, and we will have more discussion in class, and you'll get some time to practice the exercises rather. I hope it's a good evening for you folks, or a good day. Bye-bye now.